So in this problem, they ask you to provide an equation for the preparation of this compound that is shown here, and they also ask you to anticipate if there is going to be any complication with competing elimination reactions and substitution reactions. So it's a question that requires a lot of understanding that we have discussed in the classroom. So it's a simple problem on face value, but if you kind of delve deep into it, you will understand that there is more layers of complexities associated with this. So follow this closely so you can understand what exactly is going on. So this problem shows you cyclohexane structure, and that carbon and the carbon here, this carbon does not have 4 bonds, as you could see here, or 4 sigma bonds I should say. So that means this is a double bond. That's a double bond here. So that's the first thing you want to identify, because if you see a normal cyclohexane, if that's a carbon, you'll see an axial and an equatorial, whereas here you don't see that because that's a double bond. So basically you're trying to make this methylene unit on the cyclohexane, and this is basically the structure. These are the same thing, and the question is, how would you make this compound starting with any alkyl halide you want? So if you're making a double bond from an alkyl halide, obviously you need to recognize that it's a elimination reaction that you're looking at. So there are two ways to make this. One way is to take the cyclohexane, the methyl cyclohexane, and add a leaving group, say for example a bromine, on that carbon. And if you use a base like say sodium hydroxide, then you can have two possible products where you get that and that. These are the two products you would get, because for that carbon, if that is the alpha carbon, then that is one of the beta hydrogens. So beta carbon, one of the beta hydrogens, and this is a beta carbon, and that's the associated beta hydrogen. So you can lose this hydrogen to get product, say for example B, and you can lose that hydrogen to get product A. So there are these two possible products, and as we have seen in the classroom, when you use a small base and you try to execute an elimination reaction using a small base, then the ZZ product is going to be the major product, because this is the 1, 2, 3. It's a tri-substituted alkene, and this, as you could see here, that's a carbon, and there are 2 carbons attached to it, so it's a di-substituted alkene, and this is the Hoffman product. So if you start with this alkyl halide and use sodium hydroxide, you're going to get this as the major product, because that's a more substituted alkene, and this is going to be the minor product. So therefore this alkyl halide in combination with the sodium hydroxide here is not going to give you the product you're looking for, which is this one as the major product. It's going to give you that one of the isomers of this product as the major product. So this reaction, this combination of reactants will not be the right answer. Now if you take the same alkyl halide and you treat this with a bulky base like sodium tertiary butoxide or potassium tertiary butoxide, then the bulky base, as we have discussed in the classroom, is going to favor the Hoffman product, because it is going to have an easier time abstracting the hydrogen that is more exposed, that's a lower degree. So this is a primary hydrogen, primary carbon, and a primary hydrogen. That's a secondary hydrogen, and therefore the potassium tertiary butoxide will abstract that hydrogen easily. So when you use this combination of reactants, then you're going to get this as the major product. The Hoffman product is the major product in this case, and the ZZ product is going to be the minor product. So this is a appropriate answer. Now an even better way to make the same alkene, which is that one, is to take another isomer of the alkyl halide. So you can start with the leaving group on the terminal carbon. So you can start with the leaving group there, and here there is only, if this is the alpha carbon, there is only one beta carbon and there is only one hydrogen on the beta carbon. That's beta, that's alpha, beta. There is only one hydrogen here. Therefore, now if you treat this with even sodium hydroxide, let's say a smaller base, you don't need to waste a bulky base on this. If you use a small base, the small base is going to abstract that proton, that's the only one hydrogen that is there, and therefore there is only one product you will get. You will not get multiple products, and that's going to be just this. In this case, this product is not even a possibility because the leaving group is not here, the leaving group is over there. Therefore this product will not even form, and this is the only product as long as the elimination product is concerned. And this is also a correct answer. In fact, this is probably the best answer. This one is fine, is an appropriate answer, but this is going to be a better way to make this alkene here. And I asked you not to worry about having to decide between elimination and substitution reaction. Therefore, you don't have to, this problem you don't have to worry about discussing whether or not you're going to have any interference from a substitution reaction.